Hello, it's Keith here, and this is lesson 5 of the so-called Suck Hunt series of Z80 assembly programming tutorials, in which we look at my Suck Hunt stereoscopic shooter. Now, the game is a rail shooter, which is, it's an Operation Wolf style scrolling game where the game scrolls and enemies come on the screen as the level progresses. And what we're going to be looking at today is primarily sprite clipping. Now, if you see here, you can see that the moon and the clouds are going on and off the screen, as is the gun here, and they will appear partially on the screen. Now, this game will scroll to the left or to the right, but it never scrolls up or down. So effectively, we're only clipping the sides of the screen, and we will see that reflected in the sprite code. Now, before we continue discussing that, though, I just want to quickly show my book. I've written a book on assembly programming. It's called Learn Multi-Platform Assembly with Chibi Akumas. It covers Z80, 6502, 68000, 8086, and ARM. And you can get it on Amazon either in print or as a Kindle digital book if you prefer. So please take a look at that if you want to support my channel and learn about assembly programming. Anyway, we're going to go back to the game. The game, of course, is open source and free, so go to the website and download it if you want to play it, or if you want to steal the source code. Go ahead and steal the source code. I totally encourage you to do that. Anyway, the sprite clipping. So we're going to need to be able to crop the sprites so that they're partially on and partially off the screen. How do we do that? Well, what we do is we have a virtual coordinate, and we convert that to a physical coordinate. Now, the physical screen on most of the systems is 256 pixels wide. On the Amstrad CPC, it's 320 pixels wide. But we want to make sure our coordinates are always within a 0 to 255 range so that we can use a single byte. So the coordinate system I tend to use these days is 2 physical pixels to 1 logical unit. So our screen on a 256 pixel wide screen is logically 128 units wide. And on the 320 pixel wide screens, it will be 320 units wide. Now, the way we do this is we have an area that is effectively invisible at the sides of the screen, and this area isn't drawn, and any sprite that's completely in this off-screen area will not be drawn, and any sprite that's partially in that area will need to be clipped. Now, if you look here, I've got this sort of sample. If you imagine that this green area is the visible screen, and these red areas are the logical units that are not shown on the screen, the way the coordinates work is effectively this is the coordinate 0, 0 in the x and y axis, and this will be 48 units along in the x-axis is the first visible pixel, and there's 48 units here as well, which are off screen on the right hand side. Now, if our sprite was at, say, unit 16, then it might be partially on and partially off the screen, and we're going to need to clip it, and that's what we need to calculate. So we would have to calculate the number of off-screen units here, and we would need to start drawing that many units offset into the bitmap data of our sprite. And when we get to the end of the first line and we jump to the second line, we'd need to skip that many units again for each line of the sprite. For this sprite, this is on the left-hand side of the screen. On the right-hand side of the screen, we would start drawing from the very first byte of the bitmap data, but we would still need to skip the removed units from the right-hand side of the sprite as we draw the sprite to the screen. We're going to see that represented in our code today. So let's go over to the code and let's take a look. Okay, so the first thing we've got here is the definition of our logical units. On the CPC, the visible screen is 160 logical units wide. That's 320 pixels divided by 2. And the invisible borders of the screen are 48 units wide on either side of the visible screen. So anything that was drawn at a coordinate below 48 and the width of that didn't reach 48 would be completely off the screen, and we won't even attempt to draw those. But anything partially on the screen we're going to have to deal with. Now, the way that this game works, because images aren't partially on the top or the bottom of the screen, we're only cropping the sides for convenience. But if you wanted to, it should be pretty easy for you to convert this code and make it crop the top and the bottom as well, if that's what you wanted. Okay, so here is the doCrop function. We use this before we start drawing the sprite, and what it does is it will work out any changes that need to be made to the width and height of the sprite, any offset to the source bitmap data within memory that we need to draw to the screen, and any kind of skipping after each line of the bitmap data is drawn, because part of the sprite either on the left hand side or the right hand side has been removed. So a bit tricky there, but that's what we're going to do. So when this routine is called, BC will be the X and Y position that the sprite is going to be drawn in logical units. X is the height and width of the sprite in logical units, and DE is actually the memory of the sprite bitmap data, and it's going to be in 4 color 2 bits per pixel format. That's the format used on all systems, even the 16 color ones. So that's the format we use. Now when this routine exits, it will either clear the carry flag if the sprite can be drawn to the screen, whether cropped or not, or it will set the carry flag if the sprite is completely off the screen. And if that's the case, then the sprite drawing routine will just give up, because it doesn't want to draw a 0 pixel sprite. It will just be a waste of CPU power, so it will just give up in that case. Now here's the code, and here's what we're going to do. So we're going to use IY as a amount to crop off the left hand side of a sprite and an amount to crop off the right hand side of the sprite. In the case of the small sprites in this game, you'd never need to crop both sides, but you know, if you were creating some crazy code with an enormous boss sprite, maybe you would, but it's not something this needs. But that's how we're doing things. Now what we're doing here is we're taking the logical X position, subtracting the first logical visible pixel of the screen, so pixel 48, and this is effectively calculating the position of the sprite relative to the first visible pixel. Now if we've not caused any overflow there and the carry is not set, then we don't need to crop any of the pixels of the sprite. The sprite is entirely visible on the screen, but what we do is we update the X position, because we've now basically removed the logical offset of the visible screen. So we update the X position accordingly. If we have caused some kind of cropping to be required, what we're doing here is we are negating the amount that is remaining from subtracting the offset, and this will calculate the amount we need to crop from the left hand side of the screen. So we're storing that in IYL here, and then what we're doing next is we are setting the position to start drawing the sprite to 0, because part of the left hand side of the sprite is being cropped, so the first pixel we're going to draw on the screen is at the far left of the screen, so we're zeroing the X position for that. What we're doing next is we are adding the width of the sprite here, and we are comparing this to the right hand side of the screen. So we're now seeing if the sprite is going over the right hand side of the screen. So this is effectively the width of the screen. Now we've subtracted the left hand invisible part of the screen. Once again, if we've not gone over the limit there, then the sprite is entirely on the screen, so we skip this next section. But if we have caused a carry there, then part of the sprite needs to be cropped off the right hand side. So again, we're checking if the entire sprite is entirely off the screen, and we're jumping to this routine if it is. If not, then we just need to remove some of the pixels. So we're adding the number of logical units to IYH here, which is the amount of pixels to remove from the right hand side. So IYL is the left hand side and IYH is the right hand side to remove. What we do next is we take the two calculated removals and we see if either of them is non-zero. If they aren't, if both are 0, then we don't need to crop any pixels from the sprite. So we're going to skip the next bit because it would be a waste of processing power. Okay, so now what we need to do next is we need to actually calculate the removals we need to make. Now the first one we're going to do is it's self-modifying code for the platform-specific sprite drawing. Now whenever we crop anything, when we're drawing our sprite, we need to skip some of the unused pixels. Now if you imagine here, when we're drawing this sprite, these first pixels will need to be skipped from the first line, and then we will draw the remainder of the line here. But when we jump to the second line, and every successive line, we will need to skip a few of the pixels, again these ones here. This is also true of a sprite on the right hand side of the screen. We won't need to offset in for the first line of drawing, but after every line we will need to skip these pixels here. So whenever we're drawing a line, we'll need to skip the amount of pixels cropped either from the left or the right hand side as we calculate down to the next line. And that's what we're going to do next. We've got a special routine which does this for us. It's called getNextLine with clip. And this is a modified version of the getNextLine routine which updates the source bitmap data, adding the cropped data that we need to skip over. So what we're doing here is we are adding IYL and IYH, and then we're shifting them to the right by 1 bit. This is effectively halving them, and the reason for that is that our logical coordinates are calculated in pairs of pixels, but our bitmap data is just 2 bits per pixel, so there's 4 pixels per byte. So the cropping is going to be working in 4 byte chunks basically, and that's why we're doing that there. We're then storing via self-modifying code here the amount of pixels we want to clip, and then we are turning on the routine via self-modifying code that's going to do that clipping, get next line with clip, and we're replacing the next line command with that. The regular one would just move down a line within the VRAM to do the calculation for the next drawing position in VRAM. We're going to see all of this in the platform specific section later. So that's calculating the amount to skip for each line. What we need to do next is we need to update the width, because once again, if we just look at our screenshot here, the visible size, whether we've cropped the left or the right, the amount we're going to want to draw to the screen is of course much smaller. And so what we're doing here is we are taking the width, subtracting the amount cropped from the left and the amount cropped from the right, so that whichever one is cropped, we are updating the width to the new drawing width area there. And then what we're doing next is we are taking the amount that's going to be cropped from the left hand side and we are adding that here to DE, and that is effectively skipping the first number of pixels that we don't want to draw from the left hand side, because we're drawing from maybe the middle of the sprite there. We only do that for the left because the right hand side is entirely being done by that skipping routine. The left hand pixel will still be the first one there, so that's why that's different. Once we've done that, we're skipping down here to clip done. This routine is going to convert the logical units to the physical pixel location there. The no clip routine here is just doing some clear up to make sure that the stack is correct for this routine to continue running. This routine is going to be run irrespectively as long as there's some pixels to draw. So now what we're doing is we are converting the logical units to a byte position for the screen. Now on the CPC we've got 4 pixels per visible byte, so we are effectively halving the logical units to get the byte position. But on a 16 color system like the Spectrum Next, there are 2 pixels per byte, so that's effective. The logical unit is effectively the same as the byte horizontal position, but we are also doubling the Y position because there are 2 pixels per Y logical unit, but we're always working in number of lines here, so we're doubling the Y coordinate there. And then what we're doing next is we are taking the height in logical units of the sprite and the width of the logical unit of the sprite in logical units, and we're converting them up accordingly. Now the width is being calculated in bytes of the source sprite. The sprites are always 2 bits per pixel, 4 colors there, so there's no difference for the Spectrum Next or the CPC there. It still uses 4 color sprites in both cases. We're then ORing A to clear the carry, and that tells the calling routine that there is a sprite to draw. If there is no sprite to draw, if the sprite was completely off screen, we're setting the carry, and there'll be a return on carry or something like that on the routine that called this cropping routine. So that will be dealing with that and saving us hopefully some speed if the sprite is off the screen. So that's how we're cropping our sprite. What we're going to do next is look at some of the other routines that help out with the sprite system. Now the sprite data, the data that defines the sprite's position on the screen and the current frame of animation and things, we always pass by the IY register here. So this is going to get all of the settings from the sprite pointed to by IY, and it's going to load them into C and B, and also get the data address of the bitmap data into DE here. And on the MSX, that doesn't work like that. The MSX code is completely different because we're using XY coordinates within VRAM and nasty things like that. So that's slightly an exception there. But this is basically getting the coordinates of the sprite for our drawing routines when it's past a pointer in IY. Now, that will get the basic coordinates, but the other thing we need to do is we need to update frames of animation. Now these are the sprites that the game uses in AccuSprite Editor, and you can see many of the sprites just have a single object, but our sprites that are 3D, by which I mean the ones that come in and out of the screen, we store in a different format. We have basically pairs of sprites for 2 frames of animation, but then we have 3 different scales. So there's 2 frames of animation at 3 different scales, and that's how we can have our bat get closer to the screen but animate at every single stage. And that character there doesn't actually animate in that way. There's no different sizes. That one's always close to the screen. So we have those, and we have to calculate from the IY past variable the current sprite to use based on the frame of animation and also based on the current scale position, and that's what we're doing here. So we're calculating from the Z position which of the banks of sprites to use, and then what we're doing is we're multiplying by 2 and adding the frame number, which is either 0 or 1, and this is going to calculate the sprite that we want to show. And then what we're doing then is we're adding that to the sprite number as an offset, so the offset will be 0 to 5 depending on which sprite we want to show, and we are then going to calculate the new settings of the sprite. Now potentially all these sprites are different sizes, so we need to actually update the size of our sprite and the memory address of the bitmap data for that sprite to keep the sprite in the same position. The way the coordinates work in this internally is we always work from the center position of the sprite, so that as the sprite gets bigger, the object stays in the same centered position and it will go around it, rather than otherwise it would jump if it suddenly doubled in size. That wouldn't be very good. And so what we actually do is the details of the sprites here in Sprite Editor, and there's this export option here which is relatively new. If we select this export option, it will allow us to copy paste a set of ASM data, if I can just remember where it is. Here it is. And it will export this data here, and what this is an offset for the sprite based on the sprite size, the size of the sprite in pixels, and then what we can do is we can set the correct pixels per byte based on the system. So there are 4 pixels per byte for this system, and the sprite base, which is the memory address of the sprite bitmap data in RAM. So basically you can pretty much use this file, this data as is, for whatever system you're working on. You just need to change the relative size of the sprite depending on if it's 2 bits per pixel, 4 bits per pixel, 8 bits per pixel, so on, and the offset to the bitmap data, which is just here. So we're actually going to use that data, and we're going to use it to calculate the new position of the sprite. And that's what this define sprite IY does. And what this does, it takes the sprite number and it will calculate the new settings for the sprite. So this is what we're doing here. So we're getting sprite info, which is the data exported from Sprite Editor in IX. There are 4 bytes per sprite, so we're shifting to the left twice, and then we're just adding that, so we can now point IX to the data for the sprite we are wanting to set this object to, depending on its position and of animation. And we are then loading in the 2 memory addresses of the sprite here, and we're loading those into the current sprite settings. We're then loading the new width and the new height of the sprite, and we're storing those into the sprite pointed to by IY, because as I say, as the sprite gets closer to the screen it will get bigger, but it's the center that's used as the base point for the sprite within the IY data, and then the offset to the start, the top left corner, is recalculated for drawing. And you can see that those recalculations are being done here. We are loading in the width and we are shifting to the left to effectively halve that, and then we're subtracting that from the X pos and the Y pos when we're calculating the new position of the sprite in this get sprite settings from my IY function here. So that's how we're calculating the position of the sprite and how we're keeping them central at all times. So that's how we're getting the data to draw a sprite, and that's how we're updating the sprite for animation. But there is another thing, which is when we are starting the game, we want to set the sprites up. Now, the game, a lot of the sprites have a parallax depth, the background sprites at least. You'll have rocks in the foreground, and they'll have different Z layers, and they'll have different Y positions, and they'll scroll at different speeds accordingly. If your rock's in the distance, you probably want it higher up, and you want it to move slowly, and a rock to the bottom of the screen will want to visibly stick out more. That's the 3D Z position, and it will probably want to move faster. If the rock in the distance was moving faster than the rock in the foreground, that would make the perspective not work. So we've actually got a set of perspectives defined for us. Here they are. So here we've got, I think this is a Z depth, a move speed, and this is a Y position, and then there's one unused byte here. So these are the data that we're reading from, and all we're doing is we are picking a random one depending on the range of data. We're using the doRangeRandom function here, and we are selecting a random position here, and it will depend on the object. We wouldn't want a cloud to have the full range, because a cloud at the very bottom of the screen would look a bit odd unless it was very misty. So we're just doing that here. We're getting a random perspective, and then we're just setting the Z pos, the speed, and the Y pos according to one of the random objects here. And we do this B times, so we can repeat this to set lots of clouds, lots of rocks, and things like that. So this is doing the random perspective for background objects. We have a set sprites random function, which is for things like bats, which will appear anywhere on the screen. So this is more appropriate for objects that aren't limited by the perspective. And this will set either an X or a Y position, just depending on what it is passed with a pointer to. So this will randomize a single parameter in IY. The other thing we have, which is related to this, is the define sprite function. Now, those are all random settings, which is all very well and good for X and Y positions, but a lot of the settings will be constant. Your cloud object will want to have the definitions for the cloud's type of object, the sprite number. It will have a program, whether it's shootable or not, things like that. So it will have rules that are completely strict for sprites, as will bats. Bats will have settings that are constant for bats. And so what we have is this function called define sprite here, and we pass this a pointer to DE, and this is going to be the data in RAM that we want to change. So this is the sprite that we are looking to change at this point. And HL is the source data we're going to use to predefine that sprite. So you would point HL to an entry in your ROM on the ROM systems, which is the definition of the sprite. You would point DE to the data you want to change in RAM of the sprite you want to set up. And you would copy probably the initial data, the sprite number, the rules of movement for the program code, and then you would possibly want to give it some random settings after that. And that's what this does. So this is initializing the objects for our sprites. So there we go. That's all we're covering today. Basically, as I say, it's a little bit tricky, I know, all of this, but I'm afraid these kind of games are, once you get past the simple stuff of moving a small object around the screen, you start to get into some quite tough stuff. And the sprite clipping code and things is very long, and that's why I tend to tell people, just start simply, don't aim too high in the early days, because even, this game isn't particularly amazing. It's a rushed game. It could have a lot more work done on it to make it better, and I don't have time to do that, and it doesn't really warrant it. It was designed as a tech demo more than a proper game. So anyway, as I say, you're welcome to go to my website, download the source code, and you can use it in any way you want in your own projects. I don't care if you do it in commercial projects, and if you manage to make millions of dollars from it, good luck to you. That's your achievement there. As I said before, you can get my book from Amazon. There will be a link below in the comments and the description. So if you want to buy my book, please go ahead and do so. And if you want to download the source code, go ahead and grab it from the website, and of course the game as well. Anyway, I hope you've enjoyed this today. Thanks for watching.